Hello everyone, this is JL here, and today in this video we're gonna continue on with the textbook Understanding Weather and Climate by Aguado and Burt, and we're just gonna keep going through chapter 1 here. So without further ado, let's keep going. So it's Geography 1, Chapter 1, Section 2, Thickness of the Atmosphere. So here's where you have to be a little bit careful. So it says here, every child has wondered, how high is the sky? There is no definitive answer to that question. However, because Earth's atmosphere becomes thinner at higher altitudes. Okay, so obviously we don't need to write down every child has wondered. That's not really important information. But the important part is at the very end. Earth's atmosphere becomes thinner at higher altitudes. Now that's important. And a person in a rising hot air balloon would be surrounded by an atmosphere that gradually becomes less dense. Okay, so as you rise up, atmosphere becomes less dense. Okay. At some height, the air becomes so thin that the balloonist would pass out from lack of oxygen, but there would still be an atmosphere. And then there's an example there. At an altitude of 16 kilometers or 10 miles, the density of the air is only about 10% of that at sea level, and at 50 kilometers is only 1%. Even at heights of 700 kilometers above sea level, there is some air, and hence, okay, so that's important as well. Even at heights of several hundred kilometers, I want to spell it the Canadian way, sorry. Above sea level, there is some air and hence an atmosphere. However, because no universally accepted definition exists of how much air is in the given volume consists the presence of atmosphere, we have no way to establish this upper boundary. So again, the important thing here, you have to rephrase it a bit to make it make sense though. The upper boundary of the atmosphere is unknown. Maybe undetermined. Okay. Viewed from the Earth's surface, the atmosphere appears to be extremely deep. In reality, however, most of the atmosphere is contained within a shallow envelope surrounding the oceans and continents. Most of the atmosphere, oops, forgot my arrow there. Most of the atmosphere is contained within a relatively shallow envelope surrounding the oceans and continents. Okay, let's assume for the sake of discussion that the upper limit is at 100 kilometers above sea level, blah, blah, blah. By comparing this 100-kilometer thickness with the 6,500 radius, we see that the depth is less than 2% of the thickness from the center. Okay, so we really don't need to know that. Okay, just, yeah, the clouds are no thicker than the skin on an apple. Yeah, that's not going to be on a test. So, okay, so this is important probably though. Given the shallowness of the atmosphere, its motion over large areas must be primarily horizontal. Okay, the shallowness of the atmosphere, its motion over large areas must be primarily horizontal. Okay. Okay, here's some more information. Horizontal, horizontal wind speeds are typically 1,000 times greater than vertical wind speeds. However, we cannot overlook the wind's vertical motions. As you can see, here's some more information. Vertical wind speeds, small vertical displacements of air have an impact on the state of the atmosphere. Okay. Paradoxically, the least impressive motions, vertical, despite being hardest to detect and forecast, turns out to determine much of atmospheric behavior. Okay. So we can change that up. We don't want to really phrase it like that. Vertical movements of air are hard to detect and forecast, but turn out to determine much of atmospheric behavior. Again, I'm using the Canadian spelling of behavior there because I'm in Canada. Okay. So that's another section done. Geography 2, Chapter 1, Section 3, Composition of the Atmosphere. Let's see. Let's fix that. And I really don't like the automatic bullet system here. I want to just uncheck that. Stop creating automatically bullet lists. Okay, there we go. And remember to save for sure. I can't emphasize that strongly enough. I have many times forgotten to save and lost quite a bit of information, which drives me nuts. Okay. The atmosphere is composed of a mixture of invisible gases and a large number of suspended microscopic solid particles and water droplets. Molecules of the gases, Molecules of the gases can be exchanged between atmosphere and Earth surface by physical processes such as volcanic Okay, here we can probably make a list here, which makes it easier to see. Volcanic eruptions, biological processes such as plant and animal respiration, molecules can also be, let's remember to capitalize all of these things, can also be produced and destroyed by purely internal processes. Chemical reactions between the gases. Okay, so this part obviously does not really fit in with the previous, so let's move it back out. Different section, capitalized molecular. Okay. Consider a gas that is constantly being cycled between the atmosphere and Earth's surface. If we think of the atmosphere as a reserve for this gas, the gas concentration in the reservoir will remain constant, as long as the input rate is equal to the output rate. So under such conditions, we say that the concentration of the gas exists in a steady state. Okay, so obviously they've highlighted steady state there. So we should probably include this. It might be important. Gas concentration in atmosphere will remain constant so long as the input rate, the rate at which the gas moves from ground to atmosphere, is equal to the output rate. the rate which the gas moves from atmosphere to land. And then the important thing here, under such conditions, we say the concentration of the gas exists in a steady state. So that's important. Moves from ground. Okay, looks good. Okay. Although the atmospheric concentration of gas remains constant under steady state conditions, we should write that down. Although the atmospheric concentration of a gas remains constant under steady state conditions, individual molecules stay in the atmosphere for only a finite period of time before they are removed by whatever output processes are active. Yeah, it's fixed concentration here. Okay. This is moving, adding more information onto here. The average length of time that individual molecules are of a given substance remain in the atmosphere is called the residence time. The residence time is found by dividing the mass of the substance atmosphere. Oops, I spelled that right. In kilograms by the rate at which the substance enters and exits the atmosphere. In kilograms per year. The rate, I think that was what was supposed to be there. Okay. And then, thus everything else being equal, gases that are rapidly exchanged, between Earth's surface and the atmosphere have brief residence times. Do gases that have relatively low atmospheric concentration. Okay. Figure 1.2 illustrates the concept of a steady state and residence time. Parts A and B show the same mass constituting the atmospheric reservoir, with the length of the input and output arrows indicating the rates at which gases are put into and removed. Both rates are small, however, meaning that any particular molecule of the gas has a long residence time. Okay. Not really important. Okay, so that's just describing a chart they have there, picture. But this is more important here. Atmospheric gases are often categorized as being permanent or variable. Okay. Depending on whether or not their concentration is stable. Aha. So now we have permanent gases. So this is a term you have to know. are those that form a constant proportion of the atmospheric mass. And then variable gases are those whose distribution in the atmosphere varies in both time and space. Okay. And permanent gases account for the greater part of the atmospheric mass. Okay. So we can put, and also note, we don't have to exactly go in order here, but it makes sense to put this under the permanent gases section. Permanent sorry about that, for the greater part of the atmospheric mass, 99.999% occurs in nearly constant proportion throughout the atmosphere's lowest 80 km. Because of its chemical homogeny, this region within 80 km of the Earth's surface is called the Homosphere. Aha. And obviously spell check does not like that word. We'll add it to the dictionary there. Okay, and for most purposes, we consider the Homosphere virtually the entire atmosphere. Okay, so we can sort of put that in there. The Homosphere can be considered virtually the entire atmosphere. Okay. Now we have something else called the Heterosphere. Okay. Actually, I think we can actually permanent gases. So, okay, I think it should be under here. Above the Homosphere is the Heterosphere, where lighter gases such as hydrogen and helium become increasingly dominant with increasing altitude. Because its composition varies with altitude, the Heterosphere contains no truly permanent gases. Okay, let's fix this here. Heterosphere, S-P-H-E-R-E, at the dictionary. Given the small mass at these altitudes, one can focus mainly on the Homosphere. Okay, so basically saying don't need to focus too much on the Heterosphere, as it's not really that important. It's too small of a part of the atmosphere. Okay, so now we've got a little bit more information about permanent gases and variable gases. I think, given the time we have now, I think I'm just going to go through permanent gases and then we'll call it a day for this video. Okay, so there's more information. We can add it into here. Okay, the homosphere is composed mostly of nitrogen and oxygen, with small amounts of the inert gases argon and neon, and even smaller amounts of several other gases. Atmospheric nitrogen occurs primarily as paired nitrogen. Oh, excuse me. Occurs as paired nitrogen atoms bonded together to form single molecules denoted as N. Sorry. Forgot how to N2. There we go. If you want to figure out how to do that, it's I believe it's Control Shift and the underscore key there, and it lets you put a subscript or a bottom script, whatever. Okay, and then you press the same key, Control Shift there, and then it goes back to regular size. Nitrogen gas has a molecular weight of 28.02, meaning that on average the mass of one N2 oh boy, that's really annoying. Molecule is slightly in excess. Oh boy, I got my caps on. Sorry about that. Let's change it back if I can remember how to do that. Excess of a combined total of 28 protons and neutrons. Almost all N atoms contain 7 protons and 7 neutrons, but some are heavier, having 8 neutrons. As a result, the average molecular weight of N2 is slightly greater than oops, that was not intended. Greater than 28. Nitrogen is a stable gas that accounts for 78% of the volume of the permanent gases, or 75.5% of the volume of all the percent. Sorry, I read the same part twice. 7% of their mass. Difference arises because the gases have different molecular weights, but occupy the same volume. Under similar conditions. Okay. The processes that add and remove nitrogen from the atmosphere occur very slowly. It has a very long residence time, 42 million years. Despite the fact that it makes up more than 75% of the N2 has relatively little effect on most meteorological and climatological processes. If I can spell those right. So long words. No. Yeah, that's right. Climatological. But some gases, such as nitrous oxide, are quite important to Earth's climate. Okay, we're almost done here. Bear with me here. Okay, the second most dominant gas, oxygen. O, again with the subscript. Oxygen constitutes 21% of the volume of the atmosphere and 20% of the mass. Oxygen is crucial to the existence of life. Virtually all forms of life, like nitrogen, the oxygen molecules of the atmosphere consist mostly of paired atoms called diatomic oxygen. Their residence time is about 5,000 years. Together, nitrogen and oxygen account for 99% of all the permanent gases, with argon making up the most of the remainder. I believe argon is very toxic too, I believe. Removal processes are so slow for argon that its residence time is extremely long. Okay, so got through quite a couple pages there, and there's actually quite a bit more into chapter 1. And yeah, so I hope that helps you study this textbook a bit more, and as you can see, we got quite a bit done. But we'll continue this in the next video. Thanks for watching, and I hope you good luck with your studies. All right, signing out.